Good morning. My name is Nick Bridgen. I'm Chief Executive of Ferro Alloy Resources. We have a very large vanadium project in Kazakhstan, listed in London, and registered actually in Guernsey.
Nick, good to see you. It's been a while, but you've been busy. You've got an economic study out. Do you want to give us the kind of headline numbers?
Yeah, no, with pleasure. Yes, we issued the study on results on Monday. Headline numbers are net present value $749 million. That's phase one only, I have to say. Phase two is envisaged to be 3 times bigger, in other words, taking us up to 4 times bigger altogether. So, pro-ratering, which is not very scientific, we're talking about a $3 billion value company here, project here anyway. The IRR, internal rate of return, 22%, so at the very high end. And what's very interesting about it is our very low cost of production. We're in the, depending on how you calculate it, everyone does it differently, but depending on how you calculate it, we're either in the bottom decile, bottom 10%, that's putting all our products on a vanadium equivalent basis, or if you subtract the byproducts net revenues from the costs, we're at 36 US cents per pound, which is ludicrously off the scale at the bottom. So we're a very low cost producer, which gives us a very competitive position.
Right, and talk to me about, obviously, vanadium price, I think famously we've discussed, makes sense, fairly erratic pricing over the past few years. Talk about some of the things that you've focused on in terms of managing that kind of low cost, low operational cost that you've got. I mean, things like energy or logistics or whatever it is that you think has made this project.
Well, yes, two things to be said. I mean, why is our project so low cost? It's for 2 fundamental reasons. One is our ore is not the standard magnetite. 95% of the world's vanadium is made from a form of iron ore that has vanadium byproduct values in it. Sometimes those vanadium values are high enough for it to be the primary product, but it's magnetite, and that is expensive to produce from. There's lots of it, there's no shortage in the world, but the real problem with vanadium is the production cost. But ours is a sedimentary deposit, completely different, doesn't require concentration, doesn't require roasting. It's ecologically much cleaner to produce and lower cost. That's one reason. The other reason is the huge value we're now discovering. In fact, it's running, and we're discovering more value as time goes in the carbon. And the 8.5% of the deposit is carbon, and we discovered very early on that we can concentrate that up and mill it and produce a product that actually very closely simulates carbon black, which is used in making rubber as a reinforcing filler. And we've done a lot of technical work to prove that can be used in place of carbon black in making passenger vehicle tires, which is the holy grail of the rubber industry. If you can do that, you can do anything. And that has a huge value. And then, too late for the study, unfortunately. We were hoping to get it into the study, but life wasn't kind to us and things got delayed. We found another form of this material, and that is from the waste material that's not ore. There are some parts of it that have high carbon, and that can be milled, and that also behaves. It's not as good quality. It will sell a little bit more cheaply, but it's also a very big revenue stream, and that's not even in the study. So that's not in those numbers I talked to you about a minute ago. So those are the reasons why the sort of net effect of the cost of production is so low, and a very nice position to be in. Now, there's a second part to your question. If I understood it correctly, sort of how do we manage this price volatility that we've talked about before? Vanadium is an extreme case. It spends long periods of time on the floor, and it spends short periods of time at very high values. For example, the floor in real adjusted terms is about where it is now. That's about $5.50 per pound. of V2O5. Everything in the industry is measured in terms of vanadium pentoxide. And the high value, inflation adjusted, is up to about $50. So that's the range. And you have to, when you have a vanadium project, it's got to be able to survive long periods of low prices, but you'll make up, huge amounts of money when the prices are at the upper end of that range. So you can't think of it as a fixed price forecast, although we do because we have to get a net present value. The reality is that it's a variable price, and you have to sort of look at the history to assess, the likelihood of different price ranges and look at long-term averages and things. And our project survives the low prices. It still makes money, no question of it getting into financial distress, even with a decade of low prices, no problem to us. And as I say, the project then makes huge amounts of money when the price moves upwards.
Okay, so I guess it's worth, therefore, if you don't mind, exploring some of the other kind of variables in here. Like, for instance, when it comes to the geological model that you've shown, obviously you talk about it being clean, which is nice in terms of the ore body, but the things like the reserve grade, is it fairly consistent, or does that also have a kind of variability to it? I'm talking about OB1 specifically here, obviously.
Yes, OB1 is the one we've explored. We've got sort of manifestations of 7 ore bodies altogether, and 4 of them have been drilled out, but we haven't got the results of ore bodies 2, 3, and 4 yet. So we're only talking about ore body 1 out of potentially 7, and actually potentially more when more exploration is being done. So we really are only scratching the surface. But the nice thing about our deposit is that it is very consistent. It was 500 million years ago a seabed. That's the geologist's sort of front-running theory of how it was generated. And over the years, it's become folded and dried out, risen above sea level. And it's a sort of sine wave of a shape. And the top has been weathered. So it outcrops to surface in numerous places, and the ore bodies that we're mining are what's called a syncline, a sort of U-shape in cross-section, ideal for open pit. So we've got a low stripping ratio, outcropping to surface, so there's no pre-stripping to be done. The stripping ratio is about 4.4 to 1 overall. So very easy open pit mining. And the grade is consistent. There are strata within the ore body which they extend throughout all the ore bodies as far as we know, and so they vary a little bit in the thicknesses, but essentially we're dealing with the same ore in all those 7 ore bodies, and the grade is quite consistent. They all outcrop to surface. That's why they were discovered. So a very, very easy geology.
Right, and how do you go about getting that kind of certainty over that consistency of grade? Like, obviously, I've talked to some nickel companies, their step-outs are rather incredible before they kind of put together a resource. Gold companies, much smaller, tighter. When it comes to vanadium, I mean, what is the sort of spacing that you were doing on the drilling to kind of give you certainty?
Remember, this was a flat seabed extending over hundreds of kilometres probably in all directions. That's how it started life. And so it's extremely predictable. Very little sort of tectonic alteration or anything, apart from the fact that it's a sort of curvy cross-section because it's been altered that way, but there's very little faulting. So actually the drill spacing is quite wide, but SRK recommended we do some more drilling just to be sure. We did some experimental drilling to see what the variability was at very closely spaced drilling, and from that we decided what the drill spacing, or they decided what the drill spacing should be, and now we have all of ore body number 1 in the indicated category, which is good for mining from.
Right. Okay. So in terms of, again, because I think vanadium won't be known to many, so just understanding some of the basics. So I think you've used VTO5 cut off of about 0.29-ish, somewhere from
Yes,
memory.
I'm 0.3, but maybe you're right.
0.3, okay, 0.3, right, okay. What kind of commodity, because it's an equivalent, what's the kind of, what commodity price deck and recovery factors have you used to define that equivalence? And I guess how sensitive is the pit optimization
Yes,
for that?
I mean, it's originally, I mean, SRK used a process, and we generally call it whittle, but it's moved on since it's no longer a whittle. It's a program that keeps simulating the mining of one more block, and then it works out the profitability of that block. So it's an economic test rather than, it's not, you don't decide it's 0.3. You run this economic model and let the model tell you when mining one more chunk is profitable or when it's not, adding to NPV or not adding to NPV, and it just works out at 0.3.
Whittling, okay. I'll see.
But
I'll have to look that up.
Funnily enough, some of our ore would be economic even if there was no vanadium in it, because it's worth mining it for the carbon. We've always thought this project could be done as a pure carbon project. Carbon in the sense of this carbon black material.
Okay, so you've got the carbon in there, but what else have you got in there? And I guess specifically, what else have you got in there that might sort of impact the leach kinetics or the product purity? Uranium, moly?
Well, uranium and moly are the two.
Yeah, okay.
We take them out. I mean, they have an economic value. They're worth taking out in their own right, just for the economics. But you hinted at it. The main reason we take them out is for the purity of the product. And everyone worries about uranium, but actually, there's very little uranium or radioactivity in the ore. It's below background. But we take it out. We leach it out in a special sorption. Take it out of the leach by sorption, especially on something which takes the uranium and moly out together. And of course, the vanadium sorption selectively only takes the vanadium. So actually, there's no uranium in the product at all.
Okay, interesting. When it comes to obviously going from pilot R&D pilot through to production, there's always going to be changes and reconciliations. How do you go about kind of setting sort of acceptable variances between those two phases for grade, recovery, and carbon content?
Sorry, I don't really understand what you're.
Well, I'm just thinking. Obviously, people talk about like going from bench testing or piloting through to actual production. Do you see there being much variance between those two stages and phases? And if so, what would be acceptable to you to get it when you're moving to economic phase?
Yes, yeah, no, quite. Well, that's an interesting question because we ran a pilot plant. We built a 15,000 ton a year pilot plant, and we operate it continuously. And that to us was the test of the performance. And we got much higher recovery at much lower reagent consumptions than was used in the study. Now, you have to understand what we asked Tetra Tech and SRK to do. We asked them to independently verify our process. Our technicians developed the process, and we asked them to verify it. So they did They didn't use our results. They tested all the results in. It was under Tetra Tech's supervision, but the laboratory was SGS in Canada. And they, at lab scale, they got, substantially the same results, but they got, I think, 86% recovery against our, 91. So they got a lower recovery, but importantly, they had a much bigger reagent use. And we still think we're right, but we're very happy with their conclusion because, as you know, the economic result is good enough. But the result, in real life, I think is likely to be closer to our results because ours was 15,000 tons a year, not little pots on lab tables.
Okay. So in a sense, they will, if it's going to be broadly in line with what you thought it was. So the FED or EPC component that is what you use to sort of, I guess, would you report back on any changes in terms of the resource model version control or? change management to mine plan? I mean, you'll go with what they say. Is that what you're saying?
Yes, I mean the plant is being designed by what's been independently verified. That's what
Right.
underlies
Okay.
the at the moment. But there is another process called FEED, front-end engineering and design, and we will test out some of the things that we think can be improved on during that stage. So, yeah, I expect the FEED stage to come up with several enhancements and improvements. I think that the current study is extremely conservative.
Right. Okay. And do you have any sort of plans to move into sort of OB2? And if so, how do you start integrating that?
Well, the original concept was that we would do phase one and phase two. And the reason for phasing it like that was to reduce the amount of money we have to raise. As a junior mining company, raising money is always difficult. Scale up engineering is always an issue. You know, we will learn from this phase one, and no doubt the phase two plant will be better in several ways. You don't want to be mucking around with scale up commissioning issues on a huge plant. So that's why we fixed on phase one. Phase one is 8,500 tons of V2O5 a year, which is probably a bit smaller than the average project. But phase two is based on ore bodies 2, 3 and 4. Now, we haven't actually got the full ore resource assessment. We haven't got the assays back. But we've done what's called X-ray fluorescent tests, so we know where the ore bodies are. And as I said, we know roughly all the characteristics because they're the same as ore body number one. And we know that there's a huge amount there, ample to justify our conceptual phase two, which is 3 times bigger, making 4 times bigger altogether, including cumulatively. So that's the next phase after this. That's why I started off saying we have sort of 750 million in round numbers NPV of phase one, and conceptually, by extrapolation, $3 billion of value, including phase two, and more from ore bodies 5, 6, and 7, and however many more we get to by the end of it.
So how do you settle on the sort of timing of this? Like, what's going to trigger a kind of reserve update pre-FID?
Oh, well, I mean, as soon as we have the money, it's just a money thing, you know.
Right, okay. Simple as that.
We've got all the samples ready. We've done the drilling. Yeah, it's about $800,000 we estimate to get all the assaying done, and the resource estimate for ore bodies 2, 3 and 4. But of course, the priority was to get the feasibility study done on ore body number one.
Okay. Can you talk to me about the kind of mine design, you know, and operations? I mean, I can ask you a bunch of questions, or you can just give me an overall view of it. I might dip in at the end if that's okay.
You mean the process?
Well, yeah, I think it more like, so if we can get into things like in terms of, you know, ore control and pit wall angles and strip ratios, the stuff that you think is important for us to understand about the way that it's been designed.
Yes, I'm afraid I'm not a mining man or a geologist.
Okay, broadly, as has been explained to you as a board member, what are you buying into? And maybe we can have someone technical come back on and tell us all about it.
Yeah, well, the ore bodies, the broad shape is they're kilometres long, 100, 200 metres across, and the cross section is a syncline, U-shaped. So the shape of the pits is a long, fairly narrow pit. So it's I think ore body number one is 3-4 kilometres long, and we'll mine at several points along it, and it's just open pit and shovel, standard open pit mining. The SRK have done a huge amount of supervised all the geotechnical work. We drilled to find rock strength and designed the pit slopes, and so it's a standard open pit, but long and narrow, and not very deep. Maximum depth is about 150 meters.
Right. And so, okay, well, keep it generic here in the sense that things like in terms of my recollection of Kazakhstan, extreme weather conditions, have you started any kind of the all-weather access components? What about, energy into sites, exactly? What have you done so far, or when's it all coming?
Well, let me comment on the weather first of all. We're in the south of Kazakhstan. The weather is a lot easier than in the north. In the north, they have, or east, where most of the mining projects are, they have extreme weather. They have temperatures in the minus 40s regularly in winter, and over plus 40 in summer. Well, we have the high temperatures, but we have a very short and not particularly cold winter. It does go down to minus 25, but it doesn't go into the minus 30s and 40s. And it's much shorter. The winter, those freezing months are only a couple of months a year. So first of all, it's chalk and cheese so far as weather compared in East Kazakhstan. So all weather access, no problem. We don't have to do anything special to mine in winter. Just carry on. Actually, minus 25 is a nice temperature to mine at. It's regularly done in East Kazakhstan. In the previous operation I was involved in, we tended to close the mine at minus 36. That was not because you couldn't mine, but because repairing equipment and things became difficult. So no problem for weather. In the feasibility study, there's an outline design of everything. There's a sort of mine plan, all done.
But in terms of what again, I know money's been a constraint, and these are different times now. But while you've been going through this, we've talked about that on previous conversations. But so, how much work has happened to things like power lines or tailing storage facilities, etc.?
Yeah, well, tailings, of course, is a huge issue nowadays the world over. There have been some very well publicised failures. So that was a very big part of the study. And we've had professional designs, and it's all lined and built to the highest designed to the highest standards. And I can't remember the cost that was allocated to it, but $20 or $30 million or something of that order of magnitude. So tailings is a very important issue. I can't remember the
no. Well, like energy. What work has happened so far, if any?
Power lines, you were asking about.
Yeah.
We remember we operate on site today, and as part of that, building that operation, we put in a power line connecting to a very high 110 kV power line, which is only, it's adjacent to our site, but the connection point was a couple of kilometres away. And that same line can supply enough power for phase one. There'll need to be some transformer capacity added, and more switching and things, but essentially the line can be used, and we've negotiated to take the power that we need. So power is essentially done. Water, we've designed as part of the study a pipeline to bring it in from a bore field. Road access we already have. That's right up to the door. There's a metalled road that actually comes to our site, already built by Kazatomprom, which is the big uranium miner that has various mines in the vicinity. And that road links to Shieli, where there's the motorway, which actually connects from Russia, the Baltic, and Europe, right through Kazakhstan into China and to East Coast China. So it's and that road is twinned with a rail. So it's road and rail at Shieli, which is 70 kilometres along a metal roadway, and that's all done. So all the big ticket infrastructure items are already done and paid for, which is why the capital cost is quite modest as mining projects go.
Yeah. Okay. And just in sort of in the sense of trying to understand the simplicity of this, I think you've talked in the past about sort of no roasting, no pre-concentration. But can you outline sort of the kind of flow sheet from crush, grind, leach, impurity removal, purification, etc.? I mean, what does it look like?
Yeah, broadly, it's crushing, milling, and then leaching, atmospheric leaching, and then autoclave leaching. Autoclave is just under pressure. It's relatively low pressure. It's not high pressure like you get in laterite nickel or sulfide gold. It's lower pressure, but nevertheless it's an autoclave. And then that's the leaching circuit, and then the leach solutions pass through sorption towers to where as I said before, the uranium and molybdenum is taken out onto resin, and we plan to sell that to Kazakhstan because they're a uranium supplier and they have all the licenses to treat it, and then the sorption onto resin for vanadium, and then it's stripped from the resin, and we produce first AMV, ammonium metavanadate, and then it goes through a relatively low temperature oven to just drive off the ammonia, and you end up with vanadium pentoxide. Final step is a flaker to put it into a flake, which makes it easier to handle for the steel companies that'll buy it. I should say that we're aiming the current production that steel produces, that's vanadium pentoxide flake. And the reason for that is that's the most basic product and accounts for the biggest part of the market. But with very, very small changes to those final steps, we can produce different oxides of vanadium to go into battery electrolyte production, or for a very limited additional expenditure, we could make ferrovanadium. So it's really a matter of choice. The study focuses on the main product because that's where the market is most demonstrable.
Keep it simple. And you'll look at sort of capturing downstream value later. Okay. With things you just reminded me, it was at Kazakhstan. They have suffered and certainly made announcements about accessing reagent in country. I mean, for you, what does that look like at the moment?
Well,
are you confident?
Yes, it's interesting. Kazakhstan, the main reagent they use is sulfuric acid. Most of it is what they call in situ leaching, where they pump sulfuric acid underground and then collect it. So the leaching actually happens in situ underground. And they need acid. They need huge quantities of sulfuric acid. Now, our original plan several years back was that we would buy acid. There was a local producer and we were buying it. We buy it today at very low price. But we had a bit of a shock a year or two ago when suddenly there was a shortage of acid because Kazakhstan was sort of taking all the acid production, and we suddenly woke up to the fact that it wasn't sensible to rely on the market. So we incorporated a sulfuric acid plant in our plans. And although it was done of necessity to safeguard supply, it actually pays for itself because Kazakhstan, although it has a shortage of sulfuric acid, it has a huge surplus of sulfur. The cleaning up of oil production and gas production results in huge stockpiles of sulfur, which anecdotally they give away because they're paying big penalties for storing it. So we can buy sulfur, elemental sulfur, for as low as about $10 a ton. You make 3 tons of sulfuric acid from each ton of sulfur. And it's an exothermic process, so you get power out of it as well, which we use in the process. So it's a very nice thing to have your own sulfuric acid plant. It means you've got your own supply of heating and absolute certainty of supply. Sulfur is very easy to move around. It's transport's relatively easy.
Okay. Well, that's interesting. And given the kind of flow sheet you described, which sections are kind of most reagent intensive?
It's the leaching stage, the atmospheric and autoclave leaching stages.
Okay.
There are quite a lot of reagents that are needed, but sulfuric acid is the big volume one.
Right. Okay. Interesting. Should we? I think it might be worth reminding people. I know we did this last time out. It's just explaining CBS or carbon black substitute, but you did a little bit at the beginning. But can we talk about the market and some assumptions that you've made on that in terms of accessing that market?
I'm slightly repeating myself, but we got a world-renowned rubber consultancy to test the product. We started off testing it in Almaty with local professors, and they worked closely with a Belarusian university that had a rubber department. But then, for the purposes of the feasibility study, we got a UK specialist rubber consultants to test the material. And they worked out the characteristics of this. It's called a reinforcing filler. It's what makes rubber black. To make rubber, you cook up latex, a reinforcing filler like carbon black, and some silica and a few other things, additives and things, and cook it up, and that makes rubber. And the reinforcing filler, the carbon black, gives it increased bulk and wearing characteristics and all the things you want out of rubber. Latex on its own is not strong enough. And we tested our product, compared with carbon black made the traditional way, and found its characteristics. And the consultants sort of used that table of characteristics to sort of slot it into its place in the market. The better the performance, the higher the price. And so there's lots of different grades of carbon black, and one or two things that are not carbon black that are much cheaper. And by comparison of the technical performance of the material, they advised us that for tyres we could get about $500 a tonne, and for non-tyres a little bit more, largely because it's smaller volumes. Because the tyres consume about 80% of the world's carbon black, they buy in huge bulk. They can negotiate cheaper prices, and I have to say that doesn't include anything for its ecological benefit, and that could be very significant, because in Europe there are now tariffs on certain industries. It's being introduced industry by industry, but the idea is to put a carbon tax on emissions of CO2, and our material, because it's naturally occurring, we're not having to make it the traditional way like carbon black by burning hydrocarbons. So we have about 1/10 of the emissions wrapped up in what they call the embedded emissions in our product, compared with carbon black. And that means that an importer of our material into Europe or US or UK or anywhere is going to pay much less in terms of tariffs on imports. Now, this hasn't been rolled out yet fully. It has partially. So we're talking about the future, but it's the direction of travel. And those carbon credits are currently $70 a tonne, but everyone's forecasting that over time they will rise, Trump notwithstanding. So there's another $100 or $200 of value there that's not been captured in that $500 price.
Okay, so looking into the future again with you, you described some of the features, but in terms of qualifications, OEM specific qualifications or automotive manufacturers specific qualifications, who's taking you through that process or guiding you through that process so it moves from theory into reality? We're
not using a consultant-led process. What we're doing is we're finding markets which are more amenable. I think the European tyre, the biggies that we all know, we put on our cars and things, they will take some time to get used to our product, and they'll want to see our product in production before they jump, because obviously it's a huge investment for them, and a risk of a new product that they don't have a lot of sample of. But we are finding markets in China and in our region, the sort of second tier of tyre manufacturers who already use similar products to ours. They're very happy to use it, and so we'll start off on those sort of second tier companies, and I'm quite sure that over time it will move into the mainstream Western the grade A manufacturers. I mean, there's huge advantages to them in our product, mainly because they're all desperate. If you go on their websites, they're all desperate to find ways of reducing their carbon emissions. It's a big source of the world's CO2 is tyres, and there's a lot of experimentation going on with, for example, what they call recovered carbon black, where they try to recycle the tyres. Now, actually, the energy that goes into recycling the tyre is more than the energy to make the tyre. But there is a bit of a saving because there isn't the assumed burning of the tyre at the end of its life or gradual decomposition, because it's the end of life emissions that are a big part of it. But that shows the lengths they're prepared to go to. And recovered carbon black performs very badly, on that scale of usefulness to the customer in terms of its reinforcing value. It's not a good product. Ours is much better. But so we are an alternative way that they can move to hugely reduce their embedded emissions.
So what you're suggesting is that, in terms of much better, you've got an in the same way that you've designed flakes for stainless steel, for the, whether it be tire or non-tire applications, you will design in now and target certain particle sizes and morphology control and all that kind of good stuff, because broadly what they want. It's not a case of, well, let's see what they want and or produce whatever we produce and let's try and find a market. It's I design it and they shall come attitude. It's find out what the market wants and design that into our process now, in the hope of kind of going through a kind of approvals process with these groups. Yeah.
Yeah. The two products now. I haven't spelled this out. What I was describing a minute ago is the original CBS that's inside the feasibility study is based on the ore that's gone through the vanadium recovery plant, comes out of the end as tailings, and then that's our raw material that we then concentrate and mill and do a couple of other things to make it into carbon black substitute, we call it. That was the original one, and the spec of that was based on all the work that had been done initially in Almaty in Belarus, and then latterly in the UK by these consultants. The issue really is how much you substitute. If you only substitute about 10% of the carbon black with our material, there's a decent saving in cost to the company, decent saving in emissions, and the performance of the tyre is pretty much the same, unaffected by it. So it's a no-brainer to use it. For other materials, like lower quality tyres or non-tyre uses, where the performance is not critical, they can use increasing percentages of our material, as long as they've achieved the performance that they need to get for the product. Obviously, conveyor belts, tubing, other automotive parts, all those black rubbery bits that you get in cars, all have lower performance requirements than tyres, and they have, some of them need. The tests they do on rubber there's a whole battery of tests, but broadly they're ones you expect. The amount it expands before it loses its elasticity, compression, abrasion resistance, and rolling resistance. Our material is very good on rolling resistance. Tyres made from our material have a lower rolling resistance than tyres made from standard carbon black. So there's a lot of work being done to tailor our product already. And then the customers themselves, of course, all have their technical department. So the first thing they do is they get a sample from us and they test it to death. And then they decide how they can use it. And of course, there may in future be some feedback that they want a higher grade or a lower grade, or they'll pay a bit more for this characteristic. So yeah, I expect some iterative process to go on. Now, the second CBS2, which is not in the study, is not made from that material that goes through the plant. It's made from the the waste that we're already mining within the pit, but where the vanadium grade was too low to make it worth treating for vanadium, but the carbon value is still high. And
Right.
that's a whole revenue stream. It's lower grade, it's lower carbon, we'll sell it for less money, but it's still huge quantities.
So, if I may, because it seems like it's a high margin byproduct in a way, you've got to take care of core business, which is mining vanadium, extracting vanadium. But with this CBS, how much work have you done on sort of moving through to an economic state? You say they're desperate for it, but have there been conversations around firming up on pricing, indicative or non-binding offers made by any groups?
Absolutely, definitely. Yes, we have conversations going with several people who said they want it. We haven't got to the point of signing an offtake agreement, but we know, interestingly enough, that for the CBS one, the original CBS, we've really relied on the marketing study of the specialists. But for the CBS two, we've gone the other way. We found the customer first, and we didn't actually find them. The people, the original professors that we worked with in the university in Almaty, already knew of a company that was buying a similar material, and they put us in touch with them, and they're the ones that have. So it's been customer driven in a way, and we haven't. The CBS two hasn't been tested in the same way as by the UK consultants. We've just made samples of it. In fact, we're making samples of it today. We have a 400 kilos per hour test facility in our site operating today, and that's producing samples which we're sending out to China for them to look at. One particular customer has already done a lot of test work, and they love it. They've done laboratory test work. They want to, they say they want to buy it. We've negotiated a price even, but they do want to get a bit more bulk sample, so before we go ahead with it.
Okay, and how do they buy it? I don't know. You know, sense of the quantum. It's like cement market. You can buy it in bags, or you buy it in bulk tonnage. To deliveries. I mean, how's it work? And in that whole process, because it's like this. I guess you need to take care of things like moisture control or compatibility with their existing compounder lines. How does it work?
I mean, the problem for it is it's a fine powder. It's milled to 10 microns roughly, which is very fine. That makes it difficult to dry and things like that. That's why I don't get into too much in detailed technology, but that's why in the upside potential that I talked about in our feasibility study release, we have been focusing on dry milling so that we don't have the problem of drying wet fine powders. And that's a move that we will definitely be making, because we've got this 400 kilograms per hour test plant on site. We know it works. We know it's reliable. We know the power consumptions. So we know that that's a better way to go, but it was a bit too late to put it in the study.
Okay. Understood. Right. For fears of dragging this out too long or taking too much of your time, can we say what next? Okay, we've got an economic study. What next? Are we moving to working out how we finance this thing, or is there a lot more work to do before then?
There's front-end engineering and design. That's the next step. And there's two ways of doing that. We can either raise some money, conditionally for the whole project to include feed, or raise some money, with an interim raise and do feed, and then we'll have the people we're thinking of using for doing feed. We haven't made a final decision yet, but we have a very good offer from a Chinese group called, we call them for short CC6, and they will do the front-end engineering at a very good price, very good timing. That's also important. And then on the back of that, they will then quote for an EPC contract. That's the contract to build the thing. or we can go a different route where we wrap it all up with as one big funding for the whole project. But I think most likely we'll go ahead with FEED, and then we can access the much cheaper engineering and design facilities that are available locally and from China. That's the obvious way. But on the other hand, there are some interesting, because vanadium is on every Western country's critical metals list. There's quite a lot of support for Western sources of finance. So
you're going to have to pick which way you go, though, aren't you? Because you're not going to get both.
But obviously, we will keep all the doors open until we get the maximum competitive tension, and then we'll pick.
Okay. So still a few options on the table for you there in terms of the timing. They're still obviously making sure it's a competitive tension around financing, and also I guess cost of capital. Well, I appreciate the update. Maybe just finish off. So next 12 months for you, what are people looking out for?
Steps towards front-end engineering design, funding, news, CBS offtake, and there's a few other things that might come up that we're working on, but they're probably too early to talk about them.
Okay. Well, fantastic. No, appreciate the update. Stay in touch. Let us know how you get on.
Thank you.